everyone, this is Dr. Lennon, and we're going to look at logarithmic functions today. So last time we looked at exponential functions, and logarithmic functions are those functions that are designed precisely to be the inverse functions of the exponential functions. So let's define them. Definition. So we have to start with some b value, which is going to be a base. So given a b greater than 0, the logarithmic function with base b is written y equals log base b, so there's a little subscripted b here of x, and is defined in terms of an exponential equation. So, and is defined by, so y is equal to log base b of x if and only if the following equation also holds. So that's if b to the y power is equal to x. So this y that's representing the logarithm can really be thought of as an exponent in another equation. So basically, to evaluate the value of a logarithm, we just try to answer the question, what power of b makes x? Now, we won't always be able to answer this exactly from mental math, but we can for a great number of values, and that'll help us understand how to plot their graphs and get a reasonable understanding of what the value should be. But for very specific values, a lot of times we'll have to appeal to our calculator. But let's look at some examples. So just evaluating some values for logarithms before we start thinking about them as a function. So let's just evaluate. So let's start with, say, a, the log base 5 of 25. So if we're trying to evaluate that, we're basically trying to answer this question: what power of the subscripted number makes 25? And the answer there would just be 2, because 5 squared is 25. What if we did the log base 7 of, say, 1 divided by 343? Now, if you don't recognize that as a power of 7, that's okay, but basically 7 to the third power is 343, so that makes this negative 3. And why is that? This is basically because if you take 7 and you raise it to the negative third power, you get 1 over 343. What about, say, maybe the log base 8 of 1? Okay, what power of 8 would make 1? Well, that would be 0. If you take any base to the 0 power, you're going to get 1. So this is because 8 to the 0 power is indeed equal to 1. Okay, what about if we try something like d, the log base 12 of 0? Well, we get a little problem there, because really we're trying to find exponents of 12 to some power that makes 0, and if you raise 12 to any power, positive, negative, or 0, you always get a positive output value. So this is actually going to be undefined. So this is the takeaway here. Well, maybe similarly, let's add one more before we think about that. Let's say maybe we also looked at e, the log, let's say 6 of -6. This would also be undefined. So what can we conclude from examples D and E? Well, we can say the log of 0 or any negative input is undefined. So basically, when we're talking about the domain of a logarithm, the domain of the logarithm is only going to be positive real numbers. But if we talk about the range, we can get any value. So those things are a little bit different. Okay, so there's two special logarithms that we have that have their own notation. So two special logarithms. So what are those logarithms? Well, the first one is the common logarithm. So basically, if we write y equals the log of x with no base, this basically means log base 10 of x. So for the common log, the base 10 is not written, but just simply implied. And the other one that we have is the natural logarithm. So we looked at exponential functions, and we had a very important form of those exponential functions known as the continuous form. So the continuous form had a base of e, so that's exactly what the natural logarithm is going to be. So if we write y equals the natural log of x, this means log base e of x, where e is Euler's number, right? And that has value 2.71828, and it's one of those irrational numbers that continues forever, and there's no pattern that ever develops from the decimal expansion. So let's look at an example. So let's evaluate using some of these special logarithms, common logarithm and the natural logarithm. So the first one, let's just look at the log of 1,000. Okay, so what should this equal? Well, we're basically just now asking 10 to what power makes 1,000. And this is going to be 3. And this is, again, just because 10 to the third power equals 1,000. It's always easy to compute powers of 10 because basically whatever power it's raised to is how many zeros the number has behind it. Okay, maybe we'll use both sides here. What if we had the natural log of, say, the square root of e? Well, we have to ask ourselves, what exponent does the square root, what exponent stands for the square root? So that would be 1/2. So again, this is going to be because e to the 1/2 is the same thing as the square root of e. C, what if we look at, say, the natural log of 1? Well, e to the 0 power is 1 also, so this just comes out to be 0. So this is because e to the 0 is equal to 1. D, let's say we want to do the log of 1 over 100. Well, this comes out to -2, and this is essentially because 10 to the -2nd power is 1 over 100. So that's evaluating some logarithms. Let's try to draw a couple of graphs. So let's do a couple examples there. So example, so create a table of values and sketch a graph of, let's say, a y equals log base 2 of x, and also b y equals log base 1/2 of x. So this is reminiscent of what we had for exponential functions, making a table and graphing 2 to the x and 1/2 to the x. So we'll see that basically all the logarithmic graphs can kind of be broken down into the cases where the base is either between 0 and 1 or is greater than 1. So let's go ahead and first create a table of values here. So this is one of those things where we have to recall that for our table of values, we can only input things that are positive, and the only things that are going to be easy to evaluate are going to be basically powers of 2 and powers of 1/2. So let's make a table of values here for A. So our table, maybe we have x and y, which is log base 2 of x. So we can only plug in things that are positive, and those things should be powers of 2. So let's just go ahead and say 1/8, 1/4, 1/2, 1, 2, 4, and 8. So those are all powers of 2. And basically what the logarithm is going to do is it's just going to say, what power of 2 are you? Well, 1/8 is the 2 to the -3rd. 1/4 is 2 to the -2nd. 1/2 is 2 to the -1st. 1 is 2 to the 0. 2 is 2 to the 1st. 4 is 2 squared. And 8 is 2 to the 3rd. Over here for part B, we can also make a table of values. And again, these are going to be very similar values, but that's just because 1/2 is the multiplicative reciprocal of 2. So if we look at the same inputs, 1/8, 1/4, 1/2, 1, 2, 4, and 8, well, basically our outputs are just going to be the opposite sign. So 1/8 is just 1/2 to the 3rd power. 1/4 is 1/2 squared. 1/2 is 1/2 to the 1st power. 1/2 to the 0 makes 1. 1/2 to the -1 would make 2. 1/2 to the -2 would make 4. And 1/2 to the -3rd would make 8. So we can see the graphs below. Let's go ahead and just kind of sketch those out. Again, we don't really need much room for the y-axis because there's no negative y values. So we can graph both of these. So let's go ahead. We need x values. Actually, we didn't need any. So I kind of let me graph these real quick, because actually what we don't need is we don't need anything left of the y-axis. So let's maybe sketch this like this. There we go. That's a better use of space for these graphs. So our x values need to go up to 8. So I say 1, 2, 3, 4, 5, 6, 7, and 8. And the same for the x values on the other one. Okay, and our y values are going between positive 3 and negative 3, so okay. So for this first one, what happened? Well, if we think about the values, maybe we can scroll up to get them all on, or at least most of them. So at an x value of 1, we had a y value of 0. At 2, we had a y value of 1. At 4, we had a y value of 2. At 8, we were all the way up to 3. Then negative 1, we were at 1/2. And then a 4th, and then an 1/8. So pretty close. So we see this curve goes through all these dots. So it has the y-axis as a vertical asymptote, and it actually goes towards infinity. So maybe I should have used a thicker line here for this part. It's kind of tricky to draw the line here. I'll just leave it alone. Okay, so what about on the other graph? We still go through this point, 1, 0, and then we also, so at 1/2, we would have a y value of 1. Okay. 1/2, we would have a y value of 1. At a 4th, we would have a y value of 2. And at 1/8, we'd have a y value of 3. So we're still approaching the y-axis, just upward, not downward, as an example A. At 2, now we would be at negative 1. At 4, we would be at negative 2. And at 8, we would be at negative 3. So this graph kind of goes through like this. Okay, and it's a little bit tricky to draw these so nicely on the tablet here, but okay, we get the rough idea. So this is y equals the log base 2 of x, and this one right here is y equals the log base 1/2 of x. So what are some of the properties here? So basically, we could kind of like summarize the graphs. So in general, so that's it for this example with the specific values. But in general, the graphs of logs or of logarithmic functions have one of the two above shapes. So basically, 1, if your graph looks like this, if it's increasing, if it's an increasing logarithmic function, that happens when your logarithmic base is greater than 1, and 2, it has that decreasing shape if b is between 0 and 1. So those are the two shapes. What about some properties? We can list a few properties of y equals log base b of x. Okay, so 1, we could say 1 part A, the graph is increase. Well, why don't we start? We'll come back to increasing, decreasing. We should start with more fundamental things like domain and range. So 1, so the domain of any of these graphs is just 0 to infinity, positive x values, and the range is all real numbers. So the range of these graphs is negative infinity up to infinity. 3, what about, so yeah, y equals log base b of x is increasing over its entire domain. If b is greater than 1, and we could say y equals log base b of x is decreasing over its entire domain. If b is between 0 and 1. Okay, so one thing to kind of notice is, let's say a little bit about just the behavior of functions and their inverses. So this is just kind of general knowledge, but it applies particularly here between exponential functions and logarithmic functions because they are inverse functions. So let's see. So maybe we can include this as a property also. So we could say 5 y equals log base b of x passes the horizontal line test. So to be a function, you have to pass the vertical line test, but if you pass the horizontal line test, that says you are a special type of function. Thus, it is a one-to-one function. So basically, recall a function has a well-defined inverse function, meaning that the inverse is a function also, if and only if the function is one-to-one. So let's think about what that means for inverse functions in general. So the idea, so inverse functions, so the idea is to switch inputs and outputs. So if a function's a machine, so suppose f is a function, then basically if you take x and you feed it into some function machine, the function takes your input number, does something to it, and gives you an output number. So if f, so for inverse functions we use the notation -1 superscripted. This does not mean multiplicative reciprocal. That's often the mistake. So this isn't an exponent. This is just notation for inverse when we're using functions. Remember, functions are just names for things. They aren't necessarily mathematical operations when we see it performed to the name of the function, only when we see it performed to the formula. So if f inverse is the inverse of f, if you would take the output that you got above and you fed it into this inverse machine, then you would get the original input as your output. So basically the thing we can think of, this boils down to, if x comma y is on the graph of f of x, then what does that mean for the inverse function? Then y comma x is on the graph of f inverse of x. So that didn't work so well. So a result of that is basically the graph of f of x is, or how about this? The graph of f inverse of x. Let's think about it from that perspective. So the graph of f inverse of x is the reflection of f of x through the line y equals x. The reason that is the line y equals x, x values and y values are all the same. So if you flip them around, you have the same exact point. So one way to see this is, recall last time. So last time, we saw the graph of y equals 2 to the x, something like that. Looks like something like this. So today, actually it should probably be more steep. It's a little bit. It should go up a bit faster, I think. Anyway, so today we saw the graph of y equals log base 2 of x. Looks like we saw it looking something like this. So if you notice, it's not perfect, but really if you drew these on the same picture, so on the same graph, you would see that they are actually both just reflected images. So if you draw the line y equals x, the 45-degree line that passes through the origin, you have the one graph here, and you have the other graph here. So they are exactly reflections of each other. And then this line here is y equals x, this is y equals 2 to the x, and this is y equals log base 2 of x. So those are the graphs, and we see that they are in fact inverse functions. Why don't we maybe look to Desmos, and we can, just so we can see a little bit nicer picture. So if we graph y equals 2 to the x, we see we get that graph. If we do y equals x, we have the 45-degree angle line, and if we do y equals log base 2 of x, we get the other line there. So we see that, in fact, they are just reflections through that line. So if you flip them over about that 45-degree angle line, you get the same graph either way. Okay, so that's pretty much it for introducing logarithmic functions. Next time what we'll do is we'll look at some properties of logarithms and how those can be used to solve equations. That's one of the main uses of logarithms, solving exponential equations. So all the equations that we've looked at previously typically involve the exponent somewhere in the base, looking at polynomial functions. But now, if the variable is in the exponent, then we can actually use logarithms to help us solve these exponential equations. So we'll continue with that next time.